Hi there! In this tutorial, we will look at how to connect an ESP32 to your computer, run a simple blink sketch, and then we'll talk about how to use I2C communication to obtain accelerometer measurements. For your computer to identify your device correctly, you will need to install a driver. If you turn over your board, there will either be a square or rectangular black chip that has some combination of letters and numbers. These will be something similar to either CP210 or CH340. This will tell you what you need to install. In my case, I need the CH340 driver. I found it on the SparkFun website, but you can also get it off the WCH manufacturer's website. I'm on Windows, so I should be able to download and run the .exe file provided on the SparkFun website. After that, your ESP32 should be recognized and you will be able to see it in your device manager under the ports, COM, and LPT heading. Now, in order to use the ESP32 with Micropython, instead of the default, which is C++, we need to flash the Micropython firmware to the ESP32 using the Thonny IDE. This should already be done for you, but if not, you can click on Tools, Options, then Interpreter, and select Install or Upgrade Micropython, and then here you can input all of your corresponding information for your ESP32, and then just press Install. Now your computer should be able to recognize your device, and you can start writing your first program. We will first import some libraries from Micropython to make our lives easier. The machine library allows you to communicate with your device, whether it's an Arduino, ESP32, STM32, or other board. The time library lets us pause momentarily so that our instructions don't happen really quickly. Next, we will tell our microcontroller that we want pin 2 to output data. This is done by creating an instance or copy of the class pin defined within the Micropython library. We will provide it with the pin ID and pin mode to initialize it. Then, we will create a loop that runs forever, turning the LED on and off every second. On is represented by a 1 and off by a 0. Finally, we print a message to the terminal before doing it all over again. To run the program, connect your board to your computer and press the stop button to soft reboot your board, and then the green play button to run your code. Hopefully everything goes well. Now let's create a more complicated program using I2C communication and an MPU 6050. This is the main advantage of using an ESP32 or Arduino, because as great as the data acquisition cards are, they can't use I2C communication well. The MPU 6050 has a 3-axis gyroscope, accelerometer, and temperature sensor. Let's start by setting up the hardware. Connect the VCC on your MPU 6050 to 5 volts and GND to ground. SDA and SCL are the serial data and serial clock pins and should be connected to pin 21 and pin 22 respectively. You can also set them to different pins in the code. For them to function correctly, the SDA and SCL pins must have pull-up resistors. To verify that everything is connected properly, let's run an I2C scanner to check for our MPU 6050. You can copy the code from any generic Micropython I2C scanner like the one provided on GitHub. The scanner should return any I2C devices connected to our board. According to the manufacturer, our MPU 6050 should have the address 0x68. When coding microcontrollers, the main device is called the leader, and any peripheral devices are called followers. You will also hear the terms master and slave being used. Now we are ready to code. We'll start just like the last example, but we'll include some more libraries this time. ustruct will help us decipher the data we get from the MPU 6050, and the I2C class will help us to communicate using the I2C protocol. First, let's create an instance of the I2C class and specify the SDA and SCL pins and the communication frequency in Hertz. When we start the program, the accelerometer and gyroscope start in sleep mode, so we need to wake it up. We'll create a function to do this, while also configuring the accelerometer and gyroscope sensitivity. To figure out what commands we need to give the MPU 6050 to do a specific action, we have to look at a document provided by the manufacturer called a register map. Each register is associated with specific actions, and we can provide different values to a register to make it do different things. To wake up our MPU 6050, we need to access the power management register. Every register has a description of what we can control and what value we need to set each of the 8 bits to in order to accomplish this. Setting the bits like this doesn't reset the device, disables sleep mode, disables cycling, enables the internal temperature sensor, and sets the clock source to the internal clock. To access a register, we call write-to-mem from our I2C instance and give the function our follower's address, then the register we want to access, and finally the instruction we want to be performed. Unfortunately, all of these values must be in hexadecimal. We already have the MPU 6050's address, and luckily the register map gives us the register's value in hexadecimal, although this won't be the case for every register map. Now we just need to convert the binary value using an online converter. This one happens to be particularly easy. Next, let's set the accelerometer sensitivity found in the Excel config register. We don't need to activate a self-test, so we can set those to 0. The sensitivity is controlled by whatever AFS-SEL is, and let's choose a full-scale range of plus or minus 4 Gs. The register map that makes this complicated for us because they give the value as a decimal number, but we need it in binary. So we have to convert it before assigning the number to the correct bits. Now that we have our instruction, we can convert it to hexadecimal to use in our code. Don't forget the register. We can follow a similar process for the gyroscope configuration. Great, now you have all of the information you need to write instructions to the accelerometer. Now let's read some data from it. Like before, we'll create a function to do this for us. Inside the function, we can add a variable called buffer to store our raw data. Just like reading, we'll pass the follower's address and register, but instead of an instruction, we pass the number of bytes we want from the MPU 6050. A byte is 8 bits of information. In the register map, we can see that there are 6 registered allocated to accelerometer measurements. Each direction, X, Y, and Z, have 2 bytes of information associated with them. One for the most significant byte, followed by one for the least significant byte. Believe it or not, the order is important, and when the most significant byte comes first, it is called big endian. If you were to print out the raw accelerometer readings, they would be meaningless. We can use ustruct's unpack function to make the accelerometer readings understandable. We specify exactly how the data is formatted. The greater than sign specifies that the data is big endian, and the 3 H's tell the function that the raw data is made of 3 short integers. A short integer is a data type that can store values between negative 32,768 and 32,768. From the register map, we know the data is stored in the order X, Y, Z, so we will store the data to the X, Y, and Z variables in that order. Now the data is legible, but it still doesn't accurately reflect acceleration. The register map defines how to convert these numbers to proper units based on the sensitivity you chose for the accelerometer in the configuration step. Since we chose a sensitivity of plus or minus 4 Gs, our conversion factor will be 8,192 least significant bits per G. We will also multiply it by 9.806 meters per second per G to get an answer in meters per second squared. Now all we need to do is return our X, Y, and Z accelerations, loop over this function forever, and you should be done. To plot the data, Thonny IDE makes this very easy for us. If you look at the top menu, you can select View and then Plotter. Any number you print to the shell will also be plotted. If everything goes well, you should be able to place your MPU 6050 along an axis and get an acceleration of about 9.81 for one axis and values of about 0 for the other two. Thank you very much for watching, and I hope this was helpful.